Hi, hello, welcome back. This video is about operational amplifiers or we just call it op amps. Okay, so op amps are some of the most basic active components in analog systems. So I will be recording lectures about op amps maybe in three parts because op amp is a quite broad topic. Okay, so op amps are considered as some of the most basic active components in analog systems. That means you can find op amps for almost any analog applications. Okay, so just simply by connecting two external resistors, we can adjust voltage gain and bandwidth of an op amp to our exact requirements. And with using additional external other components, we can build waveform converters, oscillators, filters, and other electronic circuits that we need. Okay, so that means operational amplifiers are somewhat we call very versatile in such a way that just by placing external components to it, we can modify its applications. Okay, so for the first part of operational amplifier, this is about the introduction to operational amplifiers. Usually, op amps are already in the form of an integrated circuit. So we do not usually troubleshoot your operational amplifiers because what we see are only their pins. Okay, so we will just be discussing what is inside your operational amplifiers and how are we going to make use of your operational amplifiers. Okay, so this is the block diagram of our operational amplifier. So as you can see, it is divided into three blocks. Okay, so we have the differential amplifier and then more stages of active gains. Okay, so that means it is made up of several amplifiers which will be providing the gains for our op amp. And at the output side, it is a class B push-pull emitter follower amplifier. Okay, so usually, as we can see in the black diagram, uh, your your supply is a single-ended output. Okay, so we have here a two input. We have two terminals at the input sides. Okay, and then at the input side, and then we have a single-ended output. Okay, so since the input terminal or the input part for our differential amplifier for our op amp is a differential amplifier, your differential amplifier determines the input characteristics of our op amp. So from our previous video regarding differential amplifiers, some of the characteristics of our differential amplifiers will provide the input characteristics for our operational amplifier. And one of that is your two input terminals. So what do we call the two input terminals for operation for differential amplifiers? So we have the inverting input and the non-inverting input. So since your differential amplifier is the first stage of our op amp, we will also be using that input characteristic. So the two inputs for our operational amplifiers are also the inverting and the non-inverting, just like in your differential amplifier. Okay, and then mostly your output is single-ended. Okay, so uh, the single-ended output is designed to have a quiescent value of 0. So what do we mean by that? If we have 0 input, ideally, our result must be equal also to 0. Okay, so that is what we mean by a single-ended output design. So not all op-amps are designed like this. Okay, so some do not use a class B push-pull emitter follower at the output side, and other, they may have a double-ended output. Okay, so as you can see, since this is just a block diagram, this is not just as simple as uh, it may it may look like. Okay, so it is it usually consists of dozens of transistors. So imagine in a very small integrated circuit, it is already it is composed of dozens of transistors which are acting as current mirrors or active loads, and other innovations are still possible that other innovations are impossible if we're going to make use of discrete designs. Okay, so nowadays we are still improving out the design for our operational amplifiers. Okay, so this shows, this shows the schematic and the equivalent circuit for an op amp. Okay, so as you can see, we have there you can see there are two inputs. So just like in the differential amplifier, it is your non-inverting input and it is your inverting input. Also, as shown in the schematic diagram, it has a single-ended output. So one terminal will be provided for the output. Okay, so two terminals will be provided for the inputs. Okay, so and then, as you can see, we also have two power supplies. Okay, so you have a positive power supply, that is your plus VCC, and you also have your negative power supply, which is your negative VEE. Okay, so later on, we will be discussing that it is not just these five terminals that we are going to make use using your op amp. So there are still other terminals that we will be using. Okay, so showing also the equivalent circuit for our op-amp, this will show the characteristics for an ideal operational amplifier. So what are the characteristics for an ideal operational amplifier? So first of all, it has an infinite voltage gain. So what do we mean by an infinite voltage gain? So we are expecting really high voltage gain, so that your op amp is capable of giving us a very very high voltage gain. So it has an infinite input impedance. So if the ideal value is infinite, so therefore practical value, that means it is of a high value. Okay, so zero output impedance. So if the ideal value is zero output, so that means your output impedance is very, very low. Okay, so an ideal operational amplifier represents a perfect voltage amplifier. That's why we also call this as a voltage controlled voltage source operational amplifier, or VCVS. Okay, so as you can see, your input resistance is infinite. That means this represents an open circuit here. And then we have here your R out, which is practically equal to zero. So these are the typical op-amp characteristics. Okay, so as we can see, so this summarizes the characteristic of an ideal op-amp. So an ideal op-amp is a type of op-amp that a manufacturer would build if they could. Okay, so but since it is an ideal value, the manufacturer has just to get a value that is more closer to those ideal value. So what are the typical op-amp characteristics that we will be encountering as we go on with our discussions regarding operational amplifiers? So we have what we call the open loop voltage gain, or AVOL. So some other books that you may encounter different representation with the symbol. Okay, anyway, it is just a representation or just a symbol, but their definitions or their meanings will be the same. Okay, so we have what we call the open loop voltage gain. So we will be discussing that later. So we have the unity gain frequency, or F unity. So we have the input resistance, R in, or it can be called as input impedance with other references. So we have the output resistance or output impedance for other references. So we have the input bias current, we have the input offset current, and we have the input offset voltages. Okay, and then lastly, we have the common mode rejection ratio. So the input bias current, the input offset current, and the input offset voltage and your CMRR, we have already talked about this when we have discussed the video regarding your differential amplifier. Okay, so in this table, we have written or we have included your 741 operational amplifier. So that is your LM741C. So 741 is a standard operational amplifier. So this is a classic type of op-amp that has been available since the 1960s. Okay, so we have here open loop voltage gain. So this means we do not use any feedback or any loop. Okay, and for a 741 operational amplifier, it can have a value of as high as 100,000. So this is not an is not infinite, okay, like the ideal value, but 100,000 is such a big value for a gain. So usually when we are talking about gain in our transistor amplifiers, we're just encountered about hundreds, okay, and 100,000 here is high enough if not infinite. Okay, so so you might be wondering, what if I placed an input equivalent to 1 volt? So would I expect an output which is equivalent to 100,000? Because that is what gain is all about. Okay, so if we have an input which is equivalent to 1 volt, so what will happen to your operational amplifier? Usually operational amplifiers class are very, very small. So how do we expect it to have an output which is equal to 100,000 volts? Okay, so later we will be discussing what does that mean. But if you're going to have an input which is equivalent to 10 microvolts, there is a possibility, or it is possible, that we can get an output which is equivalent to 1 volt. So from 10 microvolts to 1 volt, that is roughly equivalent to 100,000 times. Okay, so we have a very high open loop gain. Okay, that's why we usually place a heavy negative feedback to improve overall performance of our circuit. Because it is very difficult to handle amplifiers having such a high value for your gain. So what is that negative feedback? We will be discussing that later. Okay, so unity gain frequency, so the ideal is infinite, but for LM741C, that is just equivalent to 1 megahertz. Okay, so what do we mean by that? That is up to 1 megahertz. Okay, so you can have a usable voltage gain. Okay, so maybe it we can relate this as to bandwidth. Okay, so upon reaching 1 megahertz, that is when your operational amplifier is no longer usable. Okay, so but okay, so for higher, for example, we will be needing an op amp with higher input resistance. Okay, we usually make use of a BiFET operational amplifier. So what do we mean by a BiFET operational amplifier? So BiFET is a combination of BJT and JFET. Okay, so LF157A here is an example of a BiFET op amp. So therefore, we just get the advantages of both the BJT and the JFET. So what is the advantage of BJT over JFET? So BJT is more capable of having higher gain. So that is the contribution of your BGT to your BiFET op amp. However, your JFET, on the other hand, is being used for smaller input bias and offset currents. So therefore, if you have a smaller input bias and offset currents, you have a higher input resistance. So that is the LF157A here, and it is an example of a BiFET op amp. Okay, so we have here your 741. Okay, so the 741 op amp. So, although successful, the first op amp was manufactured by the Fairchild Semiconductor in 1965, and it was called the Micro A709. So although this is considered as successful, this first generation op amp had many disadvantages. So those disadvantages led to a more improved type of op amp, which is your 741. Okay, so so you have here an example. So micro A 741. So that is an inexpensive and easy to use. Okay, so many manufacturers develop their own 741 operational amplifier. So if the op amp was manufactured by Motorola, we call this MC1741. Okay, so micro, it is from the Fairchild Semiconductor. So LM741, okay, so you might be encountering different types of integrated circuits. So the first letters in their name specifies their manufacturers. So LM741, it was being manufactured by the National Semiconductor, and SN72741, they are from Texas Instruments. Actually, this 741 op amps here, they have same specifications on their datasheets. So, what we have discussed on the previous slides, okay, from their open loop voltage gain to the input bias currents or voltages or CMRR and everything, they share the same value. Okay, so the usually the letters, the first two letters just signify what manufacturer or who manufactured that 741, but the specifications are usually the same. Okay, so why 741? Because this is the most widely used operational amplifier. And okay, and since since it is the most widely used operational amplifier, we call this as an industry standard. Okay, so what do we mean by an industry standard? Okay, so we have a rule. Okay, so that means in every design that you are going to make use, you're going to design it first by using the 741. Okay, now if once it will not meet your specific design specification, so for example, it will be needing a higher gain, or it will be needing a higher bandwidth or a higher frequency that is not within the capability of your 741, then that is just the time that you're going to upgrade to a better op amp. Okay, so now there are different versions for 741. Okay, so we have your 741, you have your 741A, 741C, 741E, or 741N. So this depends on the applications that you're going to make use for your 741. Okay, so usually they differ in voltage gain, in temperature range, in noise level, and so on. Okay, but in the laboratory or in the academe, we make use of the 741C. So your 741C is for commercial grade, okay, and this is the least expensive and the most widely used. So seen here are the three, okay, or the three most widely used package style and pin configurations. Okay, so we have here usually it is made up of 8 pins, okay, but for ceramic flat pack, it is made up of 10 pins. But usually we only make use of the 2 pins for the input terminals, okay, and then we have here for the offset null, that is from pin 1 and 2, and pin number 5, pin number 6 for your output, and pins 7 and 4 for your positive and your negative input. Okay, so we have your dual inline package, we have your ceramic flat pack, and we have your metal can package. So these are the usual package style and pin configurations being used by your 741. Okay, so this is now the simplified. Okay, so this is the simplified schematic diagram for 741. Although we cannot see this anymore because as I've mentioned, it is already in a form of an integrated circuit. We can discuss. Okay, so actually, this is not necessarily in detail form because this is already inside an IC. We just have to know the general idea on how your circuit is working. Okay, so as you can see, we have here the several pins. So we have your VCC, positive. So this is your pin number 7. We have here your negative VEE. So this is your pin number 4. We have here your V out. So this is your pin number 6. And then we have here your non-inverting and your inverting input. This is your pins number 3 and 2 respectively. Okay, so as you can see, our input terminals V1 and V2 is in a form of a differential amplifier. Okay, so if you're going to make look notice the figure, this is a differential amplifier. Okay, so it is good to know that although 741 it is usually connected to both positive and a negative supply, the op amp can still be operated using a single voltage supply. So sometimes your negative VEE can be grounded while your positive VCC input could be connected to a positive DC supply. Okay, so we will just have a brief or a fast run through with the important parameters that we can see in the simplified schematic diagram of our 741. Okay, so the input side, so the input side or the first block is actually your input differential amplifier. Okay, so later on, when we're discussing, you just go back to the circuit so that you can determine. Okay, so your differential amplifier is technically your Q1 and your Q2. Okay, so your Q14, so your Q is pertaining to your transistors, your BJT transistors. So your Q14 is a current source that replaces the tail resistor. Okay, so in an integrated circuit, it is easier to place a diode or a transistor compared to a passive components like resistors and capacitors. So instead of your tail resistor that we have discussed in the differential amplifier, we just replaced it with a current source. Anyway, we said that your tail resistor can be considered as a current source. Okay, so that is your Q14. Your R2, your Q13, and your Q14, they compose or they consist the current mirror that produces the tail current for your Q1 and your Q2, which corresponds to your differential amplifier. Okay, so your Q4 is an active load. Okay, so when we say active load, instead of using a load resistance, we make use of transistors instead. Okay, so active load Q4 acts like a current source with an extremely high impedance. So amplified signals, okay, drives the base of Q5. So your Q5 is an emitter follower. So what do we mean by an emitter follower? It doesn't really amplify. So what your input is, it will just be your output. Okay, so this avoids slowing down your differential amplifier. So the signal, okay, so the signal coming out of your Q5 goes to your Q6. Your Q7 and your Q8 is the biasing for your final stage. Q11 is also an active load, okay? So active load resistor for Q6. So your Q6 and your Q11 is a common emitter driver stage, okay, with a very high voltage gain. So anyway, common emitter, we all know that is capable of giving us a very high voltage gain. Okay, and then for the final stage, so our final stage is your Q9 and Q10. So your Q9 and Q10, they produce, or they are combined to produce our class B push-pull emitter follower. Okay? So for our quiescent output, as I've mentioned earlier, ideally it is equivalent to zero voltage when the input voltage is zero. Okay, so when you have an input voltage which is equal to zero, and you read an output voltage at the output terminal, we call that as an output error voltage. Okay, so when your V1, when your non-inverting input is greater than your inverting input, therefore we are expecting a positive output voltage. However, when your inverting input is greater than your non-inverting input, we are expecting a negative output voltage. Okay, so your output is as positive, can be as positive as VCC and as negative as your VEE. Okay, so that is the reason why, okay, when we will be inputting 1 volt, it is not possible for us to have a value which is equivalent to 100,000 volts, because your output is being limited by your source. Okay, so if our source is 15 positive and 15 negative, therefore our output will just be, okay, will just be within the maximum of positive 15 and negative 15. So the 100,000 is usually impossible, because we cannot apply a 100,000 volts to our operational amplifier. Okay, so our output is being limited by our positive VCC and our negative VEE. Okay, so if our input, for example, is positive 18 volts and negative 18 volts, then we are expecting ideally an output which is equivalent to positive 18 and negative 18. However, for practical operational amplifier, your output swing is usually within 1 to 2 volts of each supply voltage. So if our input is plus and minus 18, we are just expecting roughly around plus or minus 16 volts. Okay, so because some of our components also has voltage drop. So therefore, the positive VCC and negative VE output is only an ideal value. Okay, so what do we mean by active loading? So we have here your Q4 on the input of your differential amplifier and your Q11 in the common emitter driver stage. Okay, so active loading, so current source, we usually make use of current source. They are high output impedance. So when we say active loads, this produce much higher voltage gain than is possible with resistors, because we all know that resistors, they are capable of dissipating power, okay, and therefore they have voltage drop, so they reduces, okay, your voltage gain. That's why active loading, or using transistors as load instead of resistors, are very popular in integrated circuit. Okay, and not only that, transistors are much easier to produce or to manufacture in integrated circuits compared with resistors. Okay, so another thing that we can encounter with our operational amplifier is your frequency compensation. Okay, so we can see a single capacitor in our schematic diagram. So that single capacitor, which is CC, is what we call your compensating capacitor. Okay, so this is very, very small. Usually its value is 30 picofarad. Okay, so if you're going to remember our Miller effect, so it has an effect in our input Miller capacitance. Okay, so wherein we have your compensating capacitor multiplied by the gain plus 1. Okay, so your voltage gains here are being provided by your Q5 and Q6. Okay, so you just review the schematic diagram for where is Q5 and where is Q6. Okay, so that capacitor forms a log circuit. Okay, so what do we mean by that lag circuit? So the resistance facing the Miller capacitance is the output impedance of a differential amplifier. So due to that compensating capacitor, we have a voltage, okay, a significant voltage of 10 hertz in 741C. So what is your 10 hertz there? So your open loop gain is down 3 dB. Okay, so this suddenly becomes a cut-off frequency for your operational amplifier. Okay, so your open loop voltage gain will start to decrease or to go down uh, when it reaches the 10 hertz frequency mark. Okay, so that 10 hertz frequency mark is your 3 dB cutoff for this operational amplifier. Okay, so it says here that your open loop voltage gain decreases approximately by 20 dB per decade. Okay, so until it reaches the unity gain frequency. So for an operational amplifier 741, the unity gain frequency is equivalent to 1 megahertz. So we have here the ideal baud plot for a 741. Okay, so this is the first order response for a 741, but not all operational amplifiers are internally compensated. So not all of them have your CC inside their operational amplifier. So what do they do? Okay, so some require the user to connect an external compensating capacitor to prevent oscillations. So we have here your ideal baud plot for 741. So as you can see, we have here your 100 dB. So this is your 100,000 gain. So that starts from, since operational amplifiers, they do not use coupling capacitors, or they do not use what do you call this? They do not use a transformers, transformers at the input side. So since it's a differential amplifier, it starts with zero hertz. Okay, it starts with zero frequency. So but because of the compensating capacitor, we have here your uh, 3 dB point. Okay, so at 10 hertz, your 100 dB will start to decrease. So it will be decreasing at a rate of 20 dB per decade until it reaches your 1 megahertz frequency. So 1 megahertz is for the unity gain frequency of a 741 operational amplifier. Okay, so we have here some more terms. Actually, we have already discussed this, or we have talked about this in differential amplifier, but during that video, I have told you that we will just be focusing on the discussion once we discuss operational amplifiers. So we said an ideal op amp, when you have a zero input, supposedly our output is equal to zero. But for practical op amps, even though we don't have any input, okay, we can have an output voltage. We can read an output voltage. So that output voltage is based on your bias and offsets values. Okay, so this, because of this, they produces an output error even though we do not have an input signal. Okay, so we have what we call input bias current. This is the average of the DC base current. So it is equivalent to I in bias, which is IB1 plus IB2 all over 2. Or we have here the input offset current, which is the difference of the DC base current, I in offset IB1 minus IB2. Okay? But in the table that we have discussed a while ago, your input bias current and input offset current are usually given in the specification sheet. Okay, so we do not need to measure anymore your IB1 and your IB2. Usually, they are already pre-computed. Okay, so the input offset voltage is the input voltage that would produce the same output error voltage in a perfect differential amplifier. Okay, so your V in offset is equivalent to V error divided by your AV. Okay, so there are three errors that we are going to consider. Okay, so V1 error is due to the input bias current given by the formula RB1 minus RB2. So RB1 is the base resistance on your first input, and RB2 is the base resistance on the second input or your second transistor. Okay? And V2 error is about your input offset current, and your V3 error is your input offset voltage. So in our table a while ago, for 741, it is included. Okay? So it has a value of 80 nanoamperes, 20 nanoamperes, and 2 millivolts respectively. So once, for example, it is mentioned in the problem that a 741 op amp, so you have to know those specific values because they are standard values for a 741 operational amplifier. Now, your total error voltage will be dependent on these three, okay, multiplied by your voltage gain. Now, if we are going to make use of the open loop voltage gain, imagine 100,000, even though you have a very, very small error voltage, but if you multiply that by 100,000, we can have a very, very large amount of error voltage. That's why we do not usually make use of the open loop voltage gain. So later, we will be discussing what are we going to do to lower down that very, very high open loop voltage gain. Okay, so one way of eliminating or lowering down your offset currents is by making use of our nulling circuit. Okay, so this is usually given on the data sheet. So this works with the internal circuitry to eliminate the output error and also to minimize thermal drift. So usually, where is your nulling circuit offset null? So it is your pins 1 and 5. So usually in pins 1 and 5, we place a potentiometer. Okay, so this is our symbol for a potentiometer. Okay, so wherein we can adjust your value here so that we can eliminate. Okay, so we can eliminate your offset voltages and currents. So that is the function of your pins 1 and 5. Okay, so common mode rejection ratio. So for 741C, CMRR is 90 dB at low frequency. Okay, so it starts with 90 dB. So what is 90 dB? Okay, so if we're going to get our CMRR, so 90 dB, so 90 divided by 20, inverse logarithm. So that is equivalent to 3,106, 31,622. So that means it amplifies it amplifies your differential input 31,622 times compared with the common mode signal. Okay, so the value for 741C is 90 dB at low frequencies, and at higher frequencies it usually goes down based on the based on the graph here. Okay, so because of reactive effects, it degrades the value for your CMRR. Okay, so another thing is the maximum peak-to-peak output. Okay, so if we have, for example, a voltage which is equivalent to 30 volts, so that means positive 30 and positive 15 and negative 15, so that is peak-to-peak voltage which is 30. For ideal, your output voltage can swing almost to the supply voltage, so it is almost 30 volts peak-to-peak or plus 15 and negative 15. However, since we are dealing with non-ideal, your output voltage is somewhat smaller. So based on this, if we're going to make use a load resistance equivalent to 10 kilo ohms, the maximum that we can get is around 27 volts. So what do we mean by 27 volts? that is roughly plus or minus 13.5 volts. Okay, so the positive or the highest or the maximum value that we have at positive output that we can have is positive 13.5, and the negative output is negative 13.5. And that is if we're going to make use of a 10 kilo ohm load resistance. Using a smaller value load resistance can even have a more smaller value. So for example, we just make use of 1 kilo ohm. Okay, so if it is equal to 1 kilo ohm, so we are just roughly of about 24, or that is just a positive 12 and a negative 12 value instead of the maximum peak to peak, which is 30 volts. Okay, so that is what we mean by that is the difference between using an ideal and a non-ideal operational amplifier. Okay. So for the short circuit current, okay, so what do we mean by a short circuit current? So this is the maximum output current that the op-amp can produce. Okay, so for 741 again, its maximum current is 25 milliamperes. Okay, so it is also dependent on the type or on the value of your load resistance. So for example, you will be using a load resistance which is just equivalent to 75 ohms. So that is just equivalent to So that is just equivalent to 75 ohms. So simple Ohm's law multiplied by 25 milliamperes. So you can just have an output voltage which is equivalent to 1.87 volts. So so that we can maximize. So you just use the proper voltage or the proper resistor, load resistor, so you can maximize the values for your operational amplifier so that we can get the value of 25 milliamperes. Now, if your circuit, okay, or if your design requires a current which is higher than 25 milliamperes, therefore we cannot use your 741 op-amp because your 741 op-amp can just produce a maximum of 25 milliamperes. So how about the frequency response? Okay, so this is the frequency response for your 741 op-amp. Okay, so F unity represents the upper limit on the useful gain of your operational amplifier. So what do we mean by this? So this means that your 741 is useless above 1 megahertz. Okay, so as you can see, the lower your frequency is, the higher your voltage gain. So actually, this is really a trade-off between the gain and the bandwidth. Okay, so if you wanted a higher voltage gain, therefore, we will be using a lower bandwidth or a lower frequency. But if we wanted a higher frequency or a higher bandwidth, we will be having or we will be satisfied at a lower value of your gain. Okay, and again, if your design requires a higher frequency which is higher than 1 megahertz, so we have to choose for another operational amplifier and not the 741 because your 741 is useless above 1 megahertz. Okay, so how about slew rate? So we have here a term. Okay, so we have here a term slew rate. Okay, so where before we go to slew rate, we have to remember a while ago we have talked about the compensating capacitor. So your compensating capacitor or your CC, we needed that because it prevents oscillations that would interfere with your desired signal. However, it has a disadvantage. Okay, so since it is a capacitor, we know that it needs to be charged and discharged. Okay, so it is charging and it is discharging. So the how fast it charges or discharges creates a speed limit on how fast the output of your op-amp can change. Okay, so suppose we have an input which is a positive voltage step. Okay, so a sudden transition in voltage from one DC level to a higher DC level produces, okay, ideally this response. Okay, so for an ideal op amp, it will be producing this much. Okay, so this is your ideal response. However, okay, we have here, okay, because of the compensating capacitor that still needs to be charged and discharged, okay, before the output voltage can change to a higher level, we have here an exponential wave instead. So this is the ideal response compared with the actual, which is an exponential wave. Okay, so the slew rate, so this represents the slew rate, okay, which is the initial slope of your exponential waveform. And your slew rate is given by the formula delta V out divided by delta T. Okay, wherein your delta is change. Okay, so the change in output with respect to change in time. How fast? Okay, so this represents the fastest response that an op amp can have. For example, you change your input voltage from 0 to 5 volts. So your output, how fast your output can respond to that change. Okay, so for ideal, once I have a 0 input, I have a 0 output, and when it is 5, it is already equal to 5. But because of the compensating capacitor, it increases exponentially up to that specific 5 volts. Okay, so your slew rate represents how fast, okay, is your operational amplifier is responding when you have a positive voltage step or a sudden transition in voltage from one DC level to a higher DC level. Okay, so your slew rate is a quantity this quantity limits the large signal response of an operational amplifier. So for small output sine wave or at low frequency, it is no problem because when you say low frequency, you are changing your input slowly. Okay, so therefore, when it comes to the charging of your capacitor, it can cope up easily. Okay, so when your input is just very very small in amplitude, it can cope up easily. So the problem now lies when we have a large signal or a high frequency. Okay, because if it is high frequency, the change is in a very very high occurrence. Okay, so it is changing fastly. Okay, so the slew rate will distort, is capable of distorting your output signal. So how do we compensate for that? Okay, so we have to know your SS. So your SS is the initial slope of your sine wave. So your slew rate must be at least equal to or greater than your initial slope of your sine wave. So your sine wave is given by 2 pi f multiplied by your peak voltage. So getting the least value or the minimum slew rate requirement, so that is at least equal to, so your slew rate is equivalent to or equal to SS, which is 2 pi f VP. So in this value, we are said to be on the verge of slew rate distortion. So that means when we further increase the peak voltage or even the frequency, we can feel or we can see the slew rate distortion. So therefore, we have to know this one. And solving for F max, so this is your maximum frequency. Why? Because upon increasing this further, you can now have a slew rate distortion. And your F max is equivalent to your slew rate. Okay, so this is a characteristic. So this is a value for your op amp divided by 2 pi multiplied by VP, wherein VP is your peak voltage. Okay? And your F max is the highest frequency that can be amplified without slew rate distortion. So, other references make use of the term power bandwidth or large signal bandwidth for Fmax. Okay, so if you encounter the term power bandwidth or large signal bandwidth of an op-amp, so that refers to your Fmax. Okay, so that is the highest frequency that can be amplified without the slew rate distortion. um your 741, okay, can have a different slew rate value. Okay, so depending on your so you can have a different power bandwidth or peak voltage. It has its slew rate value. So later on we will have an example which will be related on this topic. Okay, so let's have an example. Okay, so we have here how much. Okay, so it says here how much inverting input voltage does it take to drive your 741C into negative saturation? So what do we mean by negative saturation? So that means it is negative 15 volts. Okay. However, okay, we have mentioned a while ago that when we make use of 10 kilo ohms here, okay, so when we make use of a 10 kilo ohm load, okay, so we only have a value which is equivalent to 27 volts. Okay, so when we make use of a 10 kilo ohm, just like in our example. So therefore, how much inverting input voltage does it take to drive a 741 into negative saturation? Okay, so we have here where this the 27 voltage maximum peak to peak came from. So that is from the graph that I have shown you earlier. Okay, so that is for a load resistance of 10 kilo ohms. So you have an output of a positive and negative 13.5 volts peak. Okay, and that is 27 volts peak to peak. Okay, so that means you have a positive 13.5 and a negative 13.5. So we need a negative saturation. So that means negative 13.5. So always remember that for a 741 op amp, although it is not included in the problem, but once it says 741, all of the parameters for 741, you have to know them. Okay, so because it is likewise already included in our problem. So for 741, our open loop voltage gain is 100,000. Okay, so whether it is open loop or we have a feedback resistor, what we know is that your open loop voltage gain or your voltage gain is equivalent to your V out divided by your V in. So we have your V in. So what is asked in the problem is how much inverting input. Okay, so since your input is at the inverting terminal or the negative symbol there, that means if we have a positive input, we have a negative output. So we are talking about a positive input so that it can have an output which is maximum at negative 13.5. So we don't have a new formula here, okay? So this is just the formula for your voltage gain. So this is V out divided by V in, okay? So wherein your V in is equivalent to V out, that is 13.5 divided by your voltage gain, which is 100,000, and that is equivalent to 135 microvolts. Okay, so this is the voltage, this is the maximum voltage that you can apply to your op-amp that can give you a value which is equivalent to negative 13.5. So why negative 13.5? Because in the problem, okay, so because it says here that you placed a positive input at your inverting terminal. So we expect a negative output there. Okay, so what do we mean by saturation? Okay, so what do we mean by saturation? Ma'am, what happens? So that is 135 microvolts. You multiply that by 100,000 times. It is 13.5. It is negative 13.5. So it really was amplified 100,000 times. But it will be stuck there. It will be saturated there. So what do we mean by that? Even though I placed 140 microvolts at the output, that is no longer equivalent to 140 microvolts times 100,000, because any voltage input which is greater than 135 microvolts, your output is already saturated at negative 13.5. It was already set by your input voltages. Okay, so the 100,000, you can multiply it by 100,000, all inputs that is below 135 microvolts. But once it reaches 135 microvolts and above, it will be saturated to a value which is equivalent to negative 13.5 volts. So that is what it is meant by that. Okay? Let's go to another example. So what is the common mode rejection ratio of a 741C when the input frequency is 100 kilohertz? Okay, so what do we mean by that? So if we're going to look back at this one, okay, so this is your CMRR at 90 dB. Okay, however, that 90 dB is for 0 or for 1 hertz. Okay, so what is asked in the problem is at 100 kilohertz. So all we have to do is to locate the 100 kilohertz here. And as you can see, at 1 kilohertz, our answer is 40 dB. Okay, so what do we mean by 40 dB? So what do we mean by 40 dB? So in the figure earlier, okay, so at 100 kilohertz, your CMRR is equivalent to 40 dB. So if we're going to get the CMRR out of 40 dB, okay, so that is equivalent to 40 dB, 20 log of your CMRR. CMRR is equivalent to 40 divided by 20 and then anti-logarithm. That means 100. So earlier, if it is 90 dB, it is around 31 times. So the differential input is amplifying 31 times better compared with your common mode input. Okay, however, at 100 kilohertz, your CMRR was already decreased. So it was degraded already to 40 dB. So that means only 100. So that means your differential input is amplifying was being amplified 100 times better compared with your common mode. So technically, as your frequency nears your frequency unity frequency value, your CMRR likewise decreases. Okay? So let's have another example. So what is the open loop voltage gain of a 741C? Okay, when the input frequency is 1 kilohertz, 10 kilohertz, and 100 kilohertz. Okay, so let us go back again. So let us go back again with our figure earlier, showing the frequency response. Okay, so again, as I've mentioned, it is a trade-off, okay, between the voltage gain and the frequency. As you can see, as your frequency increases, your voltage gain decreases. Okay, so they have a reverse or inverse relationship. Okay, so in our problem, we are asked to get the gain for 1 kilohertz. Okay, so for 1 kilohertz it is 100. For 10 kilohertz it is 1000. This is 100 and this is equivalent to 10. Okay, so as you noticed, 1 kilohertz to 10 kilohertz, this represents 1 decade, and from 10 kilohertz to 100 kilohertz, this also represents 1 decade. So we mentioned earlier that for a 741 op-amp, it decreases for about 220 dB per decade. Okay, so if we're going to If we're going to convert this into decibel, okay, so if you're going to convert that into decibel, so you have 1000 logarithm times 20. So this is considered, or this is equivalent to 20 dB. Okay, so 100 logarithm times 20. So this is equivalent to 40 dB. And then we have 10. Okay, 10 logarithm times 20. So this is equivalent to 20 dB. Okay, so you can see that this is increasing at a rate of 20 decibels per decade. Okay? And then if we further decrease that, okay, so if we further decrease that, after 100 kilohertz is already 1 megahertz. Okay, so after 1 decade, you can see that it will be decreasing again by 20 dB. So therefore, it is now equivalent to 0 dB. And what do we mean by 0 dB? So 0 dB corresponds to a gain which is equivalent to 1. That is why it is called the unity frequency. So that means your gain there is equivalent to 1. Okay, so your input is not yet degrading, your input is not yet decreasing, but your output is just equivalent to your input. It neither increases nor decreases. Okay? So we have here another example. So this is regarding slew rate. Okay, so this example is regarding your slew rate. So it says here the input voltage, okay? So the input voltage to an op amp is a large voltage step. Okay? So the output is an exponential waveform that changes to 0.25 in zero point 0.1 microsecond. What is the slew rate of the operational amplifier? Okay, so our slew rate is our formula for slew rate is equivalent to change in voltage divided by change in time. So it says in the problem that your waveform is changing with a rate of 0.25 volts per zero point 0.1 microsecond. So we just have to divide it. So 0.25 divided by zero point 0.1 microsecond. So that will give you 2.5 microseconds. So it means that your output is changing with respect to your input at a range of 2 at a fast rate of 2.5 microsecond. Okay? So let's have another example. So the LF 411A has a slew rate. Okay, so has a slew rate of 15 volts per microsecond. What is the power bandwidth? So power bandwidth is your F max. Okay, so what is the power bandwidth for a peak output voltage of 10 volts? Okay, so we are given the following. So we are given the slew rate. So your slew rate is equivalent to 15 volts per microsecond. We do not know your F max, we do not know your power bandwidth, but we are given your peak voltage, which is equivalent to 10 volts. Okay, so your F max is given by the formula slew rate divided by 2 pi Vp. So this is 15 volts per microsecond divided by 2 pi times 10. So this is per microsecond. So your denominator is microsecond, and 1 over time or 1 over period is equivalent to frequency. That's why our unit for F maximum is kilohertz. Okay, so by solving this, we have a value which is equivalent to 239 kilohertz. So what do we mean by this? That means if you apply a frequency which is equivalent to 250 kilohertz, for example, you can expect what you call the slew rate distortion. But below 239 kilohertz and up to 239 kilohertz, we won't be encountering your slew rate distortion. Okay, so that is what is meant by that one. Okay, so another example, we have here what is the power bandwidth for each of the following. So given a slew rate of zero point 0.5 microsecond Vp, 8, we just set it this to 8 so that we can see the effect of your slew rate, okay, with respect to a constant value of peak voltage. So again, going back here, okay, so we can see that we have here your values, okay, so just by looking at the graph, just by looking at the graph, just um by inspection, okay, so at zero point 0.5 microsecond, you have 10 kilohertz. At 5 volts per microsecond, you have 1 kilohertz. And at slew rate of 50 volts per microsecond, you have 1 megahertz. Okay, so that means as you increase or as your slew rate increases, so that means it is capable of adjusting to your input faster compared to those with a lower slew rate. So that means we can also use a frequency which is of higher value. So the higher your slew rate, the higher the frequency that is capable of adjusting to. Okay, so that is what we meant by slew rate. Okay, so those are the different parameters that we need before we can analyze circuits having operational amplifiers on it. Okay, so I have here a set work for you. Actually, this is still an operational, a differential amplifier. However, we will be now using the effect of the input bias and input offset and the input offset current and the input offset voltage. Okay, so if we have a 10 millivolts input here, what is our output error voltage? Okay, so you can make use of the values here and the values of your V1 error, V2 error, and your V3 error to get the total error for our set work about differential amplifier, because we said that your differential amplifier is really related to your operational amplifier, because your differential amplifier dictates the input characteristics for an op amp. Why? Because the input side of your op amp is made up of differential amplifier. Okay, so that's it for our first video regarding the operational amplifier. So thank you for listening, and don't forget to hit the like button after watching. Okay, so just wait for the second video regarding your operational amplifier. Thank you very much for watching, and God bless. Bye.